note that if I were to draw it on the whiteboard, okay, it seems a bit confusing. We were looking at page 405, right? Okay, so on page 405, okay, we have this curve negative 3x plus x cubed. That's right, plus x cubed. Okay. Negative 3x minus x cubed. Okay, so we were looking at 3x minus x cubed yesterday first, right? So this was the portion, okay, the one on the right side, okay, is the portion that is shown in your textbook itself, right? Then after that, okay, the derivative curve, okay, because when we derive the function, we differentiate the function y equals to 3x minus x cubed, okay, upon differentiation, we will be getting the equation 3 minus 3x squared, correct? And if I were to plot out this equation, this will be what we get. Okay, so this equation here, right, is y equals to 3 minus 3x squared. Whereas this one over here is 3x minus x cubed. Okay? So yesterday what I've been saying is that find that there is a maximum point over here which has the coordinates 1, 2. Okay? And then when at x equals to 1, okay, on the derivative curve, the first derivative curve, you find that at this point, okay, this is where your y value is equals to 0. Okay? Because we know that for the stationary point, dy dx value will be equals to 0. So in that the point is being translated to be over here, where we look at the derivative curve. Do you understand what I'm saying? Any questions? Do you understand what I'm saying? No. Can I repeat? Yes. What's the question? Okay now. Okay, so we agree that this green one over here, okay, this is our equation, original equation, right? And we see that there's a maximum point here, correct? Okay, and then this maximum point, we know that for maximum point, the derivative value will be equals to 0, right or not? Okay, so if I were to differentiate this equation, I will get the equation 3 minus 3x squared, correct? So 3 minus 3x squared, when that is equals to 0, okay, it is actually at this point, which is at x equals to 1. So we know that when x equals to 1, okay, y is equals to 2, alright, but the dy over dx will be equals to 0. Because this black curve over here, alright, this is your dy over dx curve. You understand what I'm saying? Okay, so, alright, that was what we were trying to say. Okay, then after that, if you notice, right, over the other side of the original curve, okay, we have a minimum point over here. Okay, and this minimum point, okay, so we know that the dy over dx is equals to 0. Okay, dy over dx is equals to 0 when x is equals to negative 1. So likewise on the derivative curve, okay, we find that when x equals to negative 1, dy over dx is equals to 0. You understand what I'm saying? Okay, so what conclusion are we trying to draw over here? Right, is that if I have a stationary point, okay, we know that dy over dx is equals to 0, right? Okay, and then after that, for a maximum point, which we first discussed, we observe that, okay, when translated onto a dy over dx curve, and if I were to go and look at the derivative of this dy over dx curve, which is looking at the tangent itself, okay, the tangent on the derivative curve will actually be a positive value. Okay, so we differentiate the derivative curve again, right, and that will be your second derivative. So just now, that's a negative. Negative, okay. So y equals to 3x minus 3x squared, dy over dx is actually, okay, sorry, no. What am I doing? 3x minus x squared, and then our differentiation is cubed. 3 minus 3x squared. Okay, your second derivative, the notation that we will use will be d2y over dx squared. Okay, it is the notation, it is being defined by some great mathematician, not something that I decided on. Okay, so differentiating this again, you get negative 6x. So we see that for a maximum point, the gradient of the tangent itself will be negative, and they will always happen for a maximum point. So dy over dx and d2y over dx squared, okay, and it is less than 0, it will result in a maximum point. So it's confirmed that way. Okay, so for most of the maximum points, alright, this will definitely happen. Alright, I'll explain again later why do I use the word most. Okay, then after that, if I were to look at a minimum point in this case, okay, minimum point likewise, dy over dx is equals to 0. Okay, and then after that, on the derivative curve that we have over here, okay, and I draw a tangent, I notice that this tangent has a gradient that will be positive. Okay, so d2y over dx squared more than 0, it will result in a minimum point. Right? Any questions? Any questions? No? So this is how your second derivative will work. So the whole reason we're doing second derivative, okay, is only for us to identify easily maximum and minimum point. We cannot, okay, determine whether it is an inflection point or not. Alright? It doesn't mean that when d2y over dx squared equals to 0, okay, so if I have a case like this, okay, where d2y over dx squared is equals to 0, it does not imply that it is a point of inflection. Okay, so this one we will look at try 6 and example 6 later. Okay, we will look into that later on. Okay, so this does not hold true. Alright, so my second derivative test only covers these 2 points. Okay, as in these 2 things that I mentioned. Alright, any questions? Okay, the reason why I'm doing this, okay, is for you to understand, alright, how is it that we have this understanding of the second derivative test. But of course, if you like to date memorize all your formulas and all that, I'll let you do that also can. Okay. However, before I go into doing an example, I want to just also point out, okay, notation wise, d2y over dx squared, okay, there is, you must actually present it in that way. So, okay, so the notation for second derivative, what I've used now is that we have d2y over dx squared. Okay, you could, you know that previously, if I have f prime x, that is the first derivative. It is the second derivative. Okay, it is f double prime x, not f2x. Okay, so f double prime x, it is another notation for the second derivative. Okay, but take note that this does not, okay, represent the second derivative. You cannot have dy over dx bracket square. Dy over dx bracket square simply means dy over dx times dy over dx. Okay, in our case, it is quite meaningless, right? So, but you must know the difference, okay, that this is a notation, this is an algebraic, okay, following your understanding of indices. Alright? Any questions so far? Okay. Now we look at an example. Okay, looking at try 5, we are given an equation. Okay, y equals to 2x squared minus 16x plus 27. And we're looking at the interval from 0 to 1 only. Okay? We want to find the coordinates of the stationary point on the quadratic curve. And then subsequently in part 2, we want to hence determine the nature of it. And then also sketch the curve. Okay, so to find out what is the coordinates of the stationary point, we will differentiate the given equation first, and we get 4x squared minus 16. Okay, sorry, 4x minus 16. Okay, and since we're looking at stationary point, your derivative must be equal to 0. So therefore, x is equal to 4. When x is equal to 4, we find the value of y. That will be 5. Sorry, negative 5. Okay, so for negative 5 is the stationary point. Yeah. Sorry? 0 and what? There's a question in the textbook says that. It says 0 to 8. Then maybe I copy wrong. Yours is 8. Page 406, right? Yeah. Mine says 1 then. Maybe. Now mine doesn't matter, answer still the same. Oh, because otherwise this one will not be not right. Oh. Okay. That's why textbooks are vetted by housewives. That's why we said that we will put our name onto the textbook. Right? Okay. Part 2, we want to determine the nature of stationary point. Okay, at this juncture, part 2 itself, you can definitely use the first derivative test. There's no problem about that. Okay, but let's just try to use the second derivative test. Okay. So second derivative test, we just have to differentiate this again, and that will be equals to 4. Okay, so this is clearly a positive number. So therefore, okay, this value itself will have to be a minimum point. Okay, how to actually remember this second derivative test, right? Will actually follow by how you think about your curves as well. Okay, your happy face and sad face. So this is positive, so happy face, positive, so minimum point, right? This one sad face, negative, okay, so maximum point, right? So you can remember it that way as well. Okay, you find that second derivative test, the working is definitely lesser, right? You need not draw a table like your first derivative test, okay? So this one is simple. Next, we want to sketch out the curve. So the curve itself, this is quadratic, right? And then after that, we know that 4, negative 5 is a minimum point. Okay, so you will most likely have a curve like that. Okay, then after that, it will be at 27 over here because the C value is 27. Okay. Then you need to identify what are your x-intercepts. So using your quadratic formula, you get two values, 2.42 and 5.58. 0, I'll look into it at the next example. I'll look into it in the next example. Try 6. Okay, any questions for try 5? Any questions? Alright, try 6. Okay, we are given the equation y equals to 6x to the power of 5, and then we want to find the coordinates of the stationary point and subsequently determine the nature as well. Okay, so it will be a routine to first differentiate, okay, find out what is the x value, then after that find the y coordinate. Okay. So having 0, 0 to be our stationary point, to determine the nature, let's try the second derivative test. So